Welcome to the Explainer by Forge College. I'm so glad you're tuning in. Today's Explainer marks a really critical moment in our applied solidity development journey, specifically within our module on ether and advanced state management. We are finalizing our architectural blueprints before we start pumping actual ether through the system. Now, if you recall our previous session on risk management and production readiness, we spent a lot of time locking down our safety foundation. Well, today, we're taking those safety principles, blending them with our knowledge of advanced mapping and structs usage, and stepping right into the synthesis phase. We're going to take all those brilliant, isolated code optimizations you've been working on and forge them into one single, cohesive integration manifest.
So, here's our blueprint for today's session. We'll start by blueprinting your state. Then we'll dive into the filing cabinet metaphor and move on to temperature checking data. From there, we'll hit the synthesis workflow and finally wrap up with preparing for ether flows. Let's get right into it.
All right, part one, blueprinting your state. This is all about securing that foundation before the flow begins.
Think for a second about the contrast between a totally chaotic system and an elegant one. On one side, you have a messy, scattered state. What does that actually mean? Well, it means expensive, iterative scans, fragmented data, and unpredictable gas costs that are literally going to punish your users. No one wants that, right? On the flip side, optimized retrieval is the promised land. We're talking direct keyed access, beautifully packed data fields, and deterministic storage layouts. That means every single piece of data has a mathematically guaranteed address. Replacing a clunky, expensive loop with direct keyed access, that is honestly the single most transferable skill you can develop in Solidity. Moving on to part two, the filing cabinet metaphor. Let's talk about organizing your smart contract storage. To really master organizing your smart contracts, you need a solid mental model. So let me introduce you to the filing cabinet model. It's basically a framework we use to evaluate three major aspects of smart contract state: access locality, field packing, and indirection. Instead of picturing your contract state as abstract data just floating around in the digital void, I want you to picture physical filing cabinets in a massive room. This simple model helps us instantly answer two absolutely crucial questions. Where is the exact record I need? And what specific fields of that record do I need right this second? Let's break that down. First up, the cabinet. This represents our top-level namespace, like a user's wallet address. You pull open that cabinet drawer, and inside you find a folder. That's your nested key, maybe a specific asset ID. Finally, inside that folder is the index card itself, which is the actual struct holding your data. Here's why this matters. Every single time you force a user to blindly dig around in different cabinets or pull out a massively heavy index card just to read one tiny sentence, their gas bill shoots up. And trust me, they won't be happy. The goal is to read as much as we can with just a single glance at one lightweight index card.
Which brings us to part three, data temperature. It's time to identify our hot, warm, and cold fields. As master architects, we actually need to check the temperature of our data. And here is the golden rule of state storage. Keep your hot fields slot adjacent and exile that cold, dusty metadata behind a pointer. So what's a hot field? These are the data points you are reading and updating constantly, like a user's balance. You want to pack those tightly together in your structs so they get read in a single, super cheap swoop. Cold fields, on the other hand, are the bulky, rarely accessed pieces of data, like a long text string of descriptive metadata. Shove those behind a reference pointer. You never want to make your users pay to haul freezing cold data out of storage every time they execute a simple transaction.
Of course, as an architect, you're always balancing trade-offs. If we look at our design choices here, a perfectly packed flat struct has the absolute lowest read cost for common fields. But the catch is, it's way harder to upgrade later without messing up your storage slots. Now, if you use pointers for those large fields, you introduce a moderate read cost because of the extra lookup step, but it makes it so much easier to evolve your heavy data separately down the line. Finally, normalized nested mappings give you incredible flexibility, but you're going to pay a higher gas cost if you need to do multi-lookups. So your job is simply to choose the right mechanism for the right data temperature.
All right, part four, the synthesis workflow. This is where we create that integration-ready design.
To actually build out your integration manifest, we follow a super repeatable workflow. Step one, inventory your state. Just list out every struct and mapping you currently have. Next, step two, label the temperature of every single field. Is it hot, warm, or cold? Step three, look at those freezing cold fields and swap them out for reference pointers. Step four, shape your accessors based on those gas trade-offs we just talked about. And finally, step five, map all these decisions into a concrete checklist for your actual ether flows. It's really that simple. Let's actually apply this workflow to a real scenario. Imagine we have a nested mapping going from a user to an asset to a position. Let's check the temperature. The amount and collateral inside that position, those are red hot. They get updated on every single deposit or withdrawal. The beneficiary address, we'll call that warm since it's red occasionally. But the metadata string, that is freezing cold. We almost never need it on chain. So applying our steps, we pull that bulky string out of the main struct and replace it with a lightweight bytes32 ID pointer. Think of it like a tiny digital fingerprint. Doing that is going to save everyone a literal fortune in gas.
Now, because we split that data, we also have to change how we read it. If you use a full record view, it is incredibly expensive because it hauls up the hot data alongside all that heavy, unnecessary cold data at the exact same time. We definitely don't want that. Instead, we use targeted accessors. We create a lean getPosition header function that specifically just fetches the hot amount and collateral. Then we write a totally separate getPosition metadata function that only gets triggered when someone explicitly asks for that cold data. That one simple change radically optimizes our contract reads.
And that brings us to our final section, Part 5, Preparing for Ether Flows. This is the final deliverable. This entire drafting process has been building towards one tangible climax, handing off your final deliverable. And that is a one-page integration manifest. Now, this isn't just a rough sketch or quick outline. It explicitly maps your external actions, like receiving Ether or withdrawing funds, to exact, precise storage points. So when the developer who is actually writing the Ether transfer logic takes this document, there's absolutely zero guesswork about where a balance lives or where a pointer goes.
Before we allow real money, real Ether, to start flowing through our carefully architected system, your manifest absolutely must include a few critical elements. You need exact storage locations mapped out for your balances, your escrow pointers, pending receipts, and fee accumulators. And absolutely crucial here, your reentrancy guards. Those are the digital locks that prevent hackers from double spending your funds. You really have to treat this checklist as an ironclad contract between your design and your logic.
So I want to leave you with this final provocative question. Are your blueprints fully optimized before the Ether starts flowing? Really take a hard look at your state, check the temperature of your data, and build out that integration manifest. Well, this has been an incredibly fun and insightful drafting session. Thank you so much for tuning into this explainer. If you want to dive deeper into these specific programs, practice these workflows, and master a whole host of other Web3 topics, I highly encourage you to visit forge.college to continue your learning journey. Keep building, keep optimizing, and I'll see you in the next one.